We're going to continue our discussion on multivariate calculus and optimizing functions. But in order to do that, we need to get pumped up a little. We need to go the distance.
At the starting line, engines pumping and thumping into.
All right, now that we got that going, we're ready to go. So here we have a function, and we need to optimize this function. Well, we know that the first order condition is f sub x is equal to 0, and f sub y is equal to 0. So we need to now take the partial derivative of f of x, y. And so therefore f sub x is equal to minus 14x, which comes from here, plus 88 minus, now here we have our x as our variable, and 6 and y are our constant. So it's just going to be 6y, and we set that equal to 0. Now we have f sub y. Take the partial. There's no y's here. No y's here. Now 6x is the constant, and y is the variable. So we get minus 6x plus 42 minus 4y equals 0. Now the question you're asking now is, how in the world do we solve this? Well, I'm going to bring back painful memories from algebra, where we have two variables, x and y, and two equations. So we can do a couple things. We do cancellation. So we can set our y's to the same number and just subtract them from each other. Or in this case, we can just do what you might think of as substitution. So I'm going to solve this for x. So I'm going to get negative 6x is equal to 4y minus 42. Divide by negative 6. X is equal to negative 2/3 y plus 7. So now that I have this, I'm going to substitute that in for that x right there. So we use one equation to isolate the variable and plug it into the next equation. So I get negative 14 times negative 2/3 y plus 7 plus 88 minus 6y equals 0. And now you notice, hey, this is not too bad. We have one equation, one unknown. It's not fun by any means, but we can keep going out. 28/3 y minus, do 14 times 7. We get, oh, a big number. Awesome. 98 plus 88 minus 6y is equal to 0. Okay, so I'm going to bring the y's over to one side and get here. So we get, or we'll take that to the other side rather. We get 28/3 y minus 6y is equal to 10, because 98 plus 88 is negative. It's negative 10. So now we're there. Now I'm going to multiply everything by 3. So that'll give me, oh, now we're running out of paper. Here we go. 28y minus 18y equals 30. 10y equals 30. Y is equal to 3. Awesome. But I'm not even done yet, because that's why I need to find out what x is. So coming up here, I put that at 3 in for y. So I get negative 6x plus 42 minus 4 times 3 equals 0. Now I have one equation, one unknown. Negative 6x plus 42 minus 12 equals 0. 30 equals 6x. X equals 5. So the x and y which optimize this equation is x star is equal to 5, y star is equal to 3. And that is our first order condition. And so that's the x and y that optimize this. But I want to know if it maximizes or minimizes this function. So that then leads us to our second order condition, which is fxx is either greater than or less than 0. We're not sure which. Fyy likewise. Okay? So if it's less than 0, both of these, it'll be a max. If they're greater than 0, it'll be a min. So let's look at, here is fx, here fy. So let's take the derivative of this with respect to x. So fxx is negative 14, because there's negative 14. That's 0. That's 0. Fyy is equal to, well, that's just a constant, because it's x, not y. That's a constant. That's 0. And therefore the derivative is negative 4. Both of these are less than 0. Therefore we have found a maximum. So that's how we optimize a function with two variables, a multivariate calculus problem. But now let's go back and talk about this real quick. So when we go for our first order condition, we get the system of equations. Doing all this by hand is really, that's the time-consuming process. And so what we want to do next is let's set this up in Excel and see if Excel can help us solve this much quicker. And that's exactly what we want to do. And that way we can go the distance.